All right, so today we're going to start chapter 10. We're going to begin with going over some new vocabulary and just kind of talking about three-dimensional measurement and 3D solids. So basically our first definition that we're going to talk about is a solid is a three-dimensional closed spatial figure so it's like what we see out in the world. A polyhedron is a geometric solid with polygons for faces. An edge is the intersection of two faces, and a vertex is the intersection of two or more edges. So in our diagram here, we would have this square base is a face, and then we would have four triangular faces. That would be our four triangles that make up the sides of the pyramid. The edge is going to be where like the triangles meet or where this square meets. This line here is not an edge because it goes through the center of the face. A vertex is where basically each of my edges meet. So this would be a vertex. I'd have one here, here, back here, and then the one up here. So what we're going to start talking about in this chapter first is we're going to talk about prisms first. And essentially a prism is just a figure, a geometric solid that has two congruent faces. We have two congruent faces, and we call these the bases of the prism. All other faces are called lateral faces. Right prisms are prisms where the lateral faces are perpendicular to the bases. Oblique prisms are where the lateral faces are not perpendicular to the bases. So in our notes, all of these up here would be considered right prisms because the lateral faces are perpendicular to the bases. These are all oblique prisms because the bases, the lateral faces are not perpendicular to the bases. The only other thing I can think of that we need to know would be when we go name prisms, we name them based off of the shape of the bases. So in this case, my bases here are rectangles, so we would call this a rectangular prism. These bases are triangles, so this would be a triangular prism. These bases are hexagons, so this would be a hexagonal prism. These are rectangles again, so we'd have a rectangular prism. This would be a rectangular prism. This would be a hexagonal prism because there's 6, so you get the point. The only other thing I can think of is when we talk about the height of prisms is going to be the distance, technically it's the perpendicular distance, between the bases. So if it's a right prism, the height would wind up being that lateral edge. When it's not, then they would have to tell us what that height was for that oblique prism. So essentially, we just got done with our chapter on perimeter and area. So if I would take a bunch of rectangles like this and find the area of the rectangles and stack them up, I could find the volume. So like here I have 1, 2, 3, 4, 5, 6, 7 squares tall, essentially. So I could find the area of 1 square and then take it times 7, and that would give me the volume. Same concept here. I could find the area of 1 piece of paper, that's the rectangle, figure out how many papers are in my stack, and take that area times that number, and that would give me the volume of this stack of paper. Same thing with the money, same thing with the stack of coasters. All right, so because of that, we call these stacks where we would cut the figure, we call these cross sections, where you could where the cross sections, if it's a right prism, the cross section would be the same shape as the base, because we can take all of those layers. So our formula for the volume of a prism is where you take the area of the base and just take it times the height. So this is the formula I need to memorize. It's just the area of the base times the height. Cavalieri is the guy who figured out that as long as all of the areas of the cross sections of two solids by any plane parallel to a given plane are invariably equal, then the two solids have the same volume. Basically, all what this says is that as long as each of these cross sections are the same, then I know that this volume would be the same as this volume if these cross sections are the same as all of these. So it doesn't matter if they are perpendicular or if they're slanted like this for our oblique prism. As long as each of the cross sections are the same as the cross sections here, I can find the volume. So that is what allows us to be able to have to find the volume of oblique shapes instead of right prisms. So I think of this like as long as they have the same base shape and the same height, that means that the volumes are equal. Because it's easy to find the volume of a right prism. My oblique prism, I just have to make sure that it has the same base shape and the same height as the right prism, and then I can find the volume, because the volumes would be equal. Because I just take the area of the base times the height. All right, this works, same concept, but for a cylinder. So the only difference between a cylinder and a prism is the fact that the base shape is a circle. That's the only difference. And we know how to find the area of a circle, right? The area of a circle is pi r squared. So to find the area of the volume of a cylinder, I should say volume, all we have to do is take the area of the base times the height. Well, since my base is a circle, I know I can plug in pi r squared in place of the base area to find the height. And then take it times the height. So one thing I want to talk about is typically in formulas, when we start talking about different formulas, if we use a lowercase letter, that usually means a length. So if I use a lowercase b, we're talking about the side length. If I use a capital B, this is where I'm talking about area, specifically the area of a base. Just so we know the difference between a lowercase b and an uppercase B for when we're looking at the formulas on the wall and in our notes. All right, that's it for today.